Okay, so I'll just recall what we did in the last two classes. So first we had our definition for the stochastic integral for simple functions, and where functions were it's were of this form, where like step functions, and we defined this stochastic integral with respect to the Brownian motion by just taking the steps and taking just the leftmost values and expressing it as a linear combination, and then define the stochastic integral for the closure of the span of all simple functions under the L2 of this lambda t times p norm, and then we prove the equivalent of Ito's isometry and Ito's um, the linearity and what the quadratic variation is. We prove those things, and then we saw a Riemann like we saw a way to evaluate stochastic integral using sums which are of the form of Riemann sums, and we basically took the L2 limit of uh, these Riemann sums as the norm of the partitions tends to 0 for functions which, and this was defined for functions which satisfy this mean square continuity assumption, which is that the expected the expectation of the modulus of continuity is goes to 0 as the points become closer. And then we last day we saw this small thing about localization in time. I don't want to go over it again. We saw what the closure of this space under the norm L2 lambda t cross p is. That was the set of all progressively measurable functions, and uh, then we saw then we did saw the statement of Ito's formula, basic form of Ito's formula, and we discussed some heuristics behind it. So, today I will start by showing you the proof of Ito's formula. So recall that this basic version of Ito's formula. Recall that this Ito's formula for f belong to C2 of R. This gives you a way to do change of variables, but for Brownian motion as an argument. So um, this was the statement, and so the proof. So we'll first assume that f is of compact support. F has compact support, and since it's C2, we'll assume that the sup norm of f plus the sup norm of f dash plus the sup norm of f double dash are finite, as it has compact support. And so what do we want to prove? We want to prove statements about this expression. We want to prove the statements about f of bt minus f of b 0. So we can express this as this summation so recall that These TJs are the partition points of the interval um, 0 to t, basically. So, and we are going to write this by using Taylor's theorem. We are going to write this as n of j equals to 1 to n if double dash of some zeta j's. Let's see what these are. Tj minus 1. So just these zeta j's are the term which come due to Taylor's theorem. So zeta j, they will be random, of course, for each Brownian path.
Should there be a square?
Uh, where does the square come from? Oh, sorry. Yeah. X square, yes. So zeta j of omega. So for each Brownian path, these zeta j's will change, and this is just the intermediate points. So it can be written as btj minus 1 of omega plus some theta j of omega times b tj omega minus b tj minus 1 omega, where theta j of omega is some number between 0 to 1. This is just the expression that comes due to Taylor's direct application of Taylor's theorem. And then we basically want to do it part one by one. So I want to call this term as J1, and I want to call this term as 1 by 2 times J2, or yeah, this. So, the entire summation is J1 plus half J2. So we want to claim that J1, which is this, J equals to 1 to n f dash of b tj minus 1 times b tj minus b tj minus 1. This converges in L2 of the probability measure as the norm of this partition tends to 0 to our integral 0 to t f dash of bs dbs. Now, if one remembers the last two classes, this is we have seen something similar. Basically, we want to apply that Riemann formula for evaluating stochastic integrals by Riemann sums. So this was it. So instead of this f of t, we have f of b of sj, f of b of tj minus 1. So here we had f. We would like to replace f by f of b and apply this f dash of b. Sorry, f dash of b, and apply this theorem. But we will have to prove this mean square continuity assumption for f dash of b. So we'll see how that goes.
Then it would be a random function, right? The f.
Yeah, this is a stochastic. This is just a martingale.
Okay.
this integral. This will be a martingale.
No, I mean to apply that result, did you need, if you could go back to that mean square continuity, did you need it to be a deterministic function or?
No. F was in L2 lambda t cross p.
Ah,
That
okay.
one.
Okay. Okay.
F belongs to the closure of these simple functions under that norm.
Right.
So it can be the steps. I mean, it can be random. F of omega comma t.
Ah, okay.
So so we just need to show that this. So basically, we directly have it because we assume that um, f double dash f dash the subnorm of f dash is finite. So f dash of bt uh, that would also have finite subnorm. Um, basically, so so we have the expression that we want to prove is that expectation of uh, f of bs minus f dash of bs minus f dash of bt, this uh, whole square, uh, this should go to 0 as s converges to t. So basically we have that f dash, since f dash are bounded, since f dash norm is finite, and since this p maps to f dash of bt, this is a continuous function. This means that as s converges to t, we have that f dash of bs converges to f dash of bt, and hence, and since this inner thing is bounded uniformly, we can just apply dct, and we can conclude that this expectation goes to 0. So this follows by dct, and hence we have shown that this j1 term converges to this f dash of bs dbs. So this is the, if you recall, this is the first term that comes in the Ito's formula, and now we have to show that this j2, uh, which was f double dash, right, uh, equals to 1 to n f double dash of this xi j xi j btj minus btj minus 1 whole square. So I want to further break j2 into uh, j21 and j22. So they are defined like this. Equals to 1 to n f double dash of btj minus 1 btj minus 1 whole square plus summation of j equals to 1 to n uh, f double dash of uh, psi j minus f double dash of e uh, j minus 1, and then again we have btj minus btj minus 1 whole square. Um, so first we want to note that um, if we just consider this J22, then J22 can be bounded by 2n of f double dash of minus f double dash of xij minus f double dash of b tj minus 1, and then we have j equals to 1 to n. Sorry, we just have this b tj minus also. So basically we can replace this by the maximum, because we want to use that the modulus of continuity of f double dash, so we can just replace by the maximum of all of these, minus f double dash of btj minus 1, and then we have this summation j equals to 1 to n btj minus btj minus 1 whole square. So if you now recall from what Sudesh Nadi proved a few classes back, this btj minus btj minus 1 whole square, this should converge to the quadratic variation of Brownian motion, which is t, as the uh, norm of partitions goes to 0, and that convergence should take place in L2. So basically we have something which goes to 0 times something which converges in L2 to t. So this should converge to t. So basically now we can use Cauchy-Schwarz inequality. Just write it as expectation of max 1 lesser than j lesser than n, um, f double dash of minus double dash of v tj minus 1, and we have a squared, and then we also have the expectation of this quantity. I mean, let's call this S2, which stands for the S2 stands for the two. I mean the quadratic variation, the power 2 sums. So expectation of S2 whole square. So basically, this converges to root 3, and this converges to 0, as these f double dashes are bounded. Uh, F double dash, we assume that f double dash steps would now finite, and as the norm of partition goes to 0, this xi j, this difference between the xi j and btj minus 1, this should be bounded by the modulus of continuity, and that goes to 0 as the norm of partition goes to 0. Uh, so J22, this converges to 0 uh, in L1, and we now want to prove that this J21, sorry, J21, which was summation j equals to 1 to n f double dash of btj minus 1 times btj minus btj minus 1 whole square. We want to show that this converges as norm pi goes to 0 to in L2, basically in L2 of P, to this integral test of f test of PS ds. So that would prove the Ito's formula. Um, so one second, just lost me. Yeah, so we want to show this convergence in L2. So we write expectation of um, expectation of this J21 minus equal 1 2 and f double dash of J minus 1. Uh, so recall that we can write this. We basically want to write this integral as a Riemann integral because this is a continuous function almost surely. So we can write this as a Riemann integral. So I want to write it like this: Ej minus 1. Um, and then we take the whole square. So if we show that this goes to 0, then we know that this converges to this integral of 0 to t f double dash of ds. Then we would have shown that j21 converges to this integral. Um, so this can be written as expectation of j equals to 1 to n of f double dash of b tj minus 1 times b tj minus b tj minus 1 whole squared minus tj minus 1, and then we have this entire thing squared. So now I want you to recall that bt squared minus t is a martingale. So I want to now short some notations for our ease, and I want to write this delta j b to be this btj minus 1, and I want to write delta j of t to be tj minus. Now notice that if we have that j is lesser than k, then we have tj minus 1 lesser than tj lesser than equal to tk, um, and lesser than equal to uh, yeah, sorry, this will be tk minus 1, and this is lesser than tk, and hence we have that expectation of f double dash of f double dash of b uh, tj minus 1 um, times delta jb minus delta jt, delta jb whole square minus delta jt into f double dash of b dk minus 1 into this delta k b whole square minus delta kt. So these are basically the mixed terms that occur in the, if we expand, this is the square of this summation. So if we expand it out, then these are the mixed terms that will appear. And I basically want to say that these are zero, so that we only have to deal with the square terms. So by the way, am I still audible?
Yes, you are audible.
Okay. Okay. So these are these mixed terms, as I was saying. So we want to have only the square terms survive. So we can condition. So we assume that j is less than k. So we can condition on tk on ftk first, and then take another expectation. We can write this as um, this entire thing. Expectation of this entire thing given f tk minus 1, and then we take another expectation. So basically, if we do that, since uh, so if we take with respect to tk minus 1, then these become a constant. So it becomes expectation of expectation of f so say oh sorry, yeah, j is less than k. So this can be written as b tj minus 1, if double dash of b tj minus 1 times this delta j b whole squared minus delta j t, because these are all ftk measurable, and then we'll have a further expectation of delta k b whole squared. Now, since we are conditioning on pk minus 1, we sorry, another term will come. So this b f double dash of b tk minus 1 is also measurable. So this this entire thing becomes measurable with respect to tk minus 1, ftk minus 1. So this, and then we'll have a double dash of btk minus btk minus 1, and then we'll have a further expectation of the k term delta k b whole squared minus delta k t. This and the conditioning on ftk minus 1 will vanish for this term because of Markov property, because uh, this process the s plus tk minus 1 minus btk, this btk minus 1, this process itself is independent of ftk minus 1, right? So this conditioning will vanish, and we can write it as this expectation, and this expectation is just 0 because this bt, because this is a martingale, basically bt squared minus t is a martingale, and hence we have that these terms are 0. So the only terms that survives are the squared terms, and the mixed terms vanish. So we have that J2 or J21 is expectation of J. Uh, sorry, what were we writing? Uh, we had this expression. So this expression. So we can write this as expectation of J21 minus summation J equals to 1 to n f double dash of, this is the original expression, f tj of tj minus 1, and then we have a whole square. This can be written as expectation summation of j equals to 1 to n of f double dash of b tj minus 1 whole squared times btj minus 1 uh, whole squared minus tj minus 1 whole tj minus 1, and then we have a square. So basically these mixed terms all vanished, and we are left with the squared terms. And so this term, this f double dash of b minus 1, we can just replace it by the we can upper bound it by the sup norm of f double dash. So this can be bounded by f double dash of infinity sup norm and the btj minus 1 whole squared minus tj minus 1 and then squared. But um, this is again this again should go to 0 because uh, because this basically because of continuity, btj minus 1, um, so um, we can just compute this expectation. Sorry. So btj minus 1 minus tj minus 1. So this is a normal variate. So, the variance of a normal variate, or the fourth power of a normal variate. So this will be less than equal to some c times this j equals to 1 to n of tj minus 1 whole square, right? Because the not I'm basically just computing this expectation. um, so btj minus tj minus 1 whole square, this has mean tj minus 1. So this is basically the variance of btj minus 1 whole square, and this was seen to be tj minus 1 whole squared uh, because of the properties of the normal variate, and this was even used by Sudesh Nadi in that proof of L2 convergence. And yeah, and this if this goes to 0, because this can be bounded by C times the norm of the partition times this summation j equals to 1 to n of tj minus 1, and this is just C times T times this norm of the partition, which goes to 0 as this norm of the partition goes to 0. So, so this basically tells you that for f belonging to CC2 of R, we have Ito's formula. So uh, for we have shown Ito's formula. So now the other step is just showing the extension for all C2 of R functions. So the standard way to do that is by taking these uh, those cut functions, as they are called, or bump functions. So basically, I don't want to go into the proof of that, although it's not very not at all hard, but we have to use that localization. So should I do it? Okay, let me just show it. Okay, so let this chi be um, a be a CC infinity function such that this uh, this chi is supported, is contained in minus L and L, and then we want to let FL of x equals to fx times this chi L of x, and then we can apply what we have proven to FL, and we can say that FL of Bt minus FL of B0, this is just 0 to T of FL dash of ds dbs plus half of F double dash L of what was that, ds. So now we want to have argue like this. So let tau L be the stopping time of uh, um, the first time that Brownian motion exceeds the mod of the Brownian motion exceeds the level L. So first time this happens, this stopping time, and then we let f of, now we want to use that what we proved last day, that localization, that formula, uh, yeah, this one. So this one. So remember that this stochastic integral, this is a martingale, and this stopped process, this stopped martingale can be expressed as the integral of 0 to t fs times the indicator of 0 to t 0 to tau dbs. We can express this stochastic integral as the stochastic integral of this function, this integrator, fs times this integrator. Also we can integrate with respect to this stop Brownian motion and get the same expression, get the same thing. So this is what we proved last time for discrete times, and we left out the proof of for continuous stopping continuous continuous real valued stopping times. So we want to use that and say uh, that f of the f of b t mean tau l um, minus f of b0. So this is the stop. We are stopped. We are considering the. We want to stop this. We want to consider the f of this stop Brownian motion. So this can be. This is the same as um, 0 to t mean tau l of fl dash of ds dbs plus 1 by 2 times 0 to p mean tl of fl of fl double dash of bs ds, and this can be basically rewritten as 0 to t of fl dash of ds, and we replace this replace this t mean tau l by this indicator, um, indicator of 0 to tau l, tau l dbs plus half of 0 to t fl double dash of ds indicator 0 to tau l ds. So by the way, this has not this is just basic calculus. This has nothing to do with so these towels are random. So this is just ordinary integral of a continuous function, of random continuous function. So whenever, so whatever be the value of towel, we will only integrate up to this towel. We don't want to integrate further. So this is just basic calculus. This has nothing to do with stochastic calculus or anything. This is what we proved last time. This thing. So now uh, we have that. So since we are now fixing this, we recall that this chi L's were supported in minus LL. So once we are in this, once the time is lesser than tau L, this FLs are the same as F, right? Because these chi L's were supported in minus LL, and the Brownian motion does not, uh, the mod of Brownian motion does not cross that minus LL boundary before this time tau L. So this is the same as 0 to t of f dash of bs, indicator of 0 to tau L, sorry, 0 to tau L dbs plus half 0 to t f double dash of ds, indicator 0 to tau L ds, and now again we reapply that localization, that lemma that we proved, or the theorem that we proved last time, and we write this as t mean tau L f dash of ds dbs plus half 0 to t mean tau L f double dash of ds ds. So now we just want to let these towels go to infinity, and since we have that towel goes to infinity almost surely, right? And these if dash and if double dash, we assume that uh, So yeah, so as towels go to infinity, and this holds for all L. So this is just an almost sure identity that this is equal to f dash of ps dvs plus half of 0 to t f double dash of ds ds. So so this basically proves Ito's formula for f belongs to C2. So uh, I want to basically tell you some things about the general Ito processes. So, and I want to go into some heuristic discussion now, not anything rigorous. So, Ito processes. So, and we want to introduce the concept of stochastic differentials. So, if an Ito process xt is an Ito process, if it can be written as xt equals to x0 plus 0 to t of sigma s dds. So okay, let me just write sigma s omega dds plus 0 to t of ds ds. So or again, b can be random. So these are Ito processes, um, and we, for simplicity, will assume that this sigma belongs to that L2 of lambda t cross t for all t greater than 0, and this b omega s, this is again um, L1, this is L1 of this 0 to t, because otherwise these integrals might not make sense. So so what are stochastic differentials? Stochastic differentials are basically a shortened way to write these uh, these these functions like xt. So so these dxt's. So this so a shortened way to write this uh, this expression is to write it like this. This is equal to sigma of omega t d dt plus d of omega t d. So this this should this represents the martingale part of this process xt, and this dt, this is the drift part. So this is basically where you see all those these terms like d. Whenever you take the difference stochastic differential of a process, what it basically means is that it is the um, it what it basically means is that the full the expanded expression of that is like this, is something like this. So see, this b can could have been any martingale, and this s could have been um, the increasing process of the quadratic variation of that martingale for general stochastic integrals, but this is what we will mean by taking stochastic differentials. And um, so this is a shorthand, basically a shorthand notation, and basically this notation is what is used in all of stochastic calculus. I mean, uh, people don't really write these whole expressions. They prefer these ones. Um, so now maybe there is just 5 minutes left. So uh, maybe I'll just say a few things about what we are actually missing out when we are only looking at Brownian motion instead of um, general martingales. And also we have a much more general form of Ito's formula for these Ito processes. So instead of Brownian motion, we could have replaced this by xt, f of xt minus f of x0, and we could have come up with some sort of some expression for this. So I will do that, but uh, I it's better to first state some things that we might be missing out when we are just looking at Brownian motions. So, for example, this Ito integral, this can be defined, or this stochastic integral, this can be defined for general semi-martingales. So, what are semi-martingales? Semi-martingales are just uh, semi-martingales are just processes of the form xt equals to mt plus at, where mt is a continuous local martingale and at is a increasing process. Sorry, at is a finite variation process. It's not necessarily increasing. It's a finite variation process, which means that if you define mu of 0t to be at, then this nu will define a radon measure on the real line, and there are other characterizations of it, but we can define this stochastic integral for semi-martingales, and we can state the most general form, or the most useful form of Ito's formula for semi-martingales. And uh, there are even more generalizations when you go into local times, and there's even more general Ito's formula. But I think I'll not go any further today. And next day, what I'll do is I'll state the Ito's formula for these Ito processes and discuss some things, and uh, maybe and then I'll say some heuristics about that as well and then maybe we can discuss the Ito formula for semi-martingales, and then maybe we can see the sketch of the proof, because proving it for in the full general case will take too much time. So maybe that's the plan we will stick with. So the main thing is that we want to get used to the expressions instead of so knowing the expression for semi-martingales is powerful, is very powerful, and the proof can be very unnecessarily complicated. So it's maybe we'll just sketch the proof and this just look at the expressions first and maybe have a heuristic discussion about it. So I would like to stop here today. So does anyone have any questions?
Yeah, no, I don't have any questions.
So was
Okay.
it understandable? I mean,
Yeah,
today
yeah.
the proofs are a little difficult. Uh,
No, I could understand. I mean, definitely the first half of that, and then yeah, I mean, I understand it got technical, but I could follow some part of that.
yeah, that is why I don't really want to go into too much of too much into the details of the proof, as those
Yeah,
can
yeah,
just be read.
right, right.
Yeah,
Yeah.
it's better to
No, no,
just
no.
discuss.
Yeah, yeah.
But
It was
this
good.
but this formula for Brownian motion, this is the simplest one that we prove,
Right.
and
Right.
so that's why I wanted to prove.
Yeah, yeah. I
Just
mean,
show this proof
there's
of.
no point. Yeah, I mean, ideally, would want to do continuous time martingales with second with bounded variation and all those things. But
Yeah, yeah, yeah,
yeah, the proofs would be, and I agree that they would be very ugly. Yeah,
yeah.
they should. I mean, if you are able to work with Brownian motion, that would be then enough.
Yeah, that's why. So the next day maybe I'll just. So the thing is that the theory for semi-martingale. So once we are familiar with Brownian motions, the expressions that come for Brownian motions, the thing is
Right.
that the expressions for semi-martingales will become very natural. I mean, you could sort of predict by just looking at it what the expressions will that would arise.
Yeah.
That's why I started doing the things in Brownian
Yeah.
first. So
No.
once we go into that, so things I think they will seem very natural instead of like um, going doing those first and then seeing Brownian motion. I think uh, that would be more understandable.
Right. No, this was good. I'll try to work on some problems involving it, and by the next time
Yeah, so I have I have many problems in stock actually. So uh,
Okay. If you could post it on the group, I'd like to try them. I mean,
okay, okay. So
I'm usually going through the Stack Exchange and whatever I could come across, and just
yeah, yeah.
uh,
So I have many answers on Stack Exchange in this topic. So I
okay,
can maybe uh, just upload those links
sure,
or the.
sure.
Okay.
Okay, great.
Thank you.
Thank you, Argadeep. Thank you for this. I think this is the first time I've seen, and probably the only time I will see the proof of Ito's theorem. So thank you for that.
Thank you.
Yeah. Bye. Thank you all.
Yeah, bye.
Yeah, thank you. Bye.
Thank you. Yes, bye.